I think it starts with electrification. The shift from ICE powertrains to electrified powertrains has really accelerated, and that in turn really is enabling software-defined vehicle for the first time, and so it's picking up the pace for our transition to software-defined vehicles.
When we talk about a software-defined vehicle, it isn't just a matter of putting software in a car. We do that today. That's been done for many years. A software-defined vehicle has to have a hardware platform, the physical architecture that it can run on.
And if you don't have the right compute architecture, it's hard to enable a software-defined vehicle. If you have a very distributed architecture, you can't have the features and functions coming through software where a lot of the OEMs and customers want to go. Even if the hardware architecture is modernized, you have to pick the right software architecture that works with it.
A containerized software architecture, a real-time operating system that can be safety certified to ASIL D, and a fully integrated DevOps environment, cloud native, that supports that software development all the way through its life cycle, from development, deployment, to operation.
These are the things we think we need to develop, deploy, and operate software in the field for full lifecycle management.
There are several challenges that the industry faces with ADAS systems. One is the availability of that system.
We see such a demand driven by just first regulations for safety, so lower levels of features is just driven by regulations, and level 0, level 1 features are basically going to become standard across the world.
How do we deliver those incremental features, bring the system capability up over time, but also do it at a cost where the end consumer can afford it?
Leveraging the strengths of radar is really critical because it allows you to supplement vision and supplement other sensors to really create a full, robust perception system that works when it's nighttime, it works if there's glare, it works if there's rain, it works if there's fog. These are actually not edge scenarios. They occur all of the time. And so you need the system to be really robust against all of these scenarios.
So what we're doing is we're driving the cost of those systems down by using machine learning in our radar to really increase the capability of those sensors so I can deliver that performance over all operating conditions at a lower cost. When we include AI and machine learning techniques, it allows them to see the world in much greater detail than ever before.
It's actually significantly more expensive for OEMs to build electric vehicles than it is to build an ICE vehicle, and they're mandated to hit certain targets in terms of electric vehicles by 2025 and by 2030. Anything we can do to help them bring cost out of that transition and reduce cost while maintaining performance and optimizing performance of these key devices, that's a really big contributor to their ability to profitably navigate the shift to electric vehicles.
It's really been the evolution of the physical architecture, the electrical architecture, the compute, the centralization of compute, the movement to zonal architecture. We're seeing that broadly adopted now. What that does is it simplifies the interconnect, the distribution of the power, it simplifies the cooling and the thermal properties and the packaging of that in the vehicle.
Increasingly, the differentiation and new features are coming through software. They're more software defined. It's the software architecture that works with that hardware architecture to really enable software-defined vehicles.
Nobody else in the industry is doing this. Aptiv is now the only company that can truly bring that to our customers.